Welcome to Microfluidics 1. Today we are talking about fluid dynamics. Fluid dynamics plays a very important role in many different areas. For example, in meteorology, in industry, or in microfluidic devices. Today we are going to take a deeper look at those phenomena. At the end of the lecture, you should be able to name the governing equations of fluid dynamics and explain the physical meaning of the different terms. Additionally, you can make reasonable assumptions and simplifications to the Navier-Stokes equations for a given fluidic problem. You should also be able to analytically solve the simplified Navier-Stokes equations for certain examples. And finally, you can describe the characteristics of microfluidic flow. As you can see, today's lecture consists of 4 videos. In the first video, which you're watching right now, I will give you a short introduction to fluid dynamics and discuss some basics. The second video will deal with the derivation of the continuity equation, and the third video with the derivation of the momentum equation. In the fourth video, we are going to take a detailed look at the Navier-Stokes equations. These fundamentals will be complemented by some examples we are going to look at in the actual lecture. Let's take a look at the governing equations of fluid dynamics. The governing equations are the basic conservation equations. The first one is the mass conservation, which we also refer to as the continuity equation. The second one is the momentum conservation. And the third one is the energy conservation, which is needed if thermal effects are considered. Today we are going to focus on the first 2 equations, which are called the Navier-Stokes equations. The Navier-Stokes equations is basically a set of partial differential equations that relates the density field of a fluid to the velocity field and the corresponding pressure distribution. And the Navier-Stokes equations cannot be solved analytically without simplifying assumptions. Later in this lecture, we are going to solve the Navier-Stokes equations for some very specific problems. On this slide, you can see the Navier-Stokes equation in tensor notation. As you can see, the first equation is basically the mass equation, which we're going to derive in the following video. The second equation is based on the conservation of momentum, and in one of the videos, we are going to derive this formula. What you must be aware of is that the Navier-Stokes equations look different depending on your chosen coordinate system. The question is, why should you work in non-Cartesian coordinate systems? And the reason is pretty simple. Sometimes non-Cartesian coordinate systems can reduce the complexity of a problem. For example, a problem with a rotational symmetry becomes 2-dimensional if cylindrical coordinates are used. Just imagine a pipe. A pipe has a rotational symmetry, so if you use a cylindrical coordinate system, the Navier-Stokes equation becomes 2-dimensional. But if you describe this problem in Cartesian coordinates, you would need 3 dimensions. On the right-hand side, you can see maybe the most famous example of a non-Cartesian coordinate system. It's spherical coordinates. So if you want to know your location on Earth, you would never use a Cartesian coordinate system. Instead, you would use the here depicted concept of latitude and longitude. And this is, the most common example for a spherical coordinate system. So in this course, we are mostly going to discuss problems in Cartesian coordinates, but from time to time, you may encounter cylindrical coordinates. So I just showed you the Navier-Stokes equation in tensor notation. And then I mentioned all those different coordinate systems, and you might wonder, what is the actual aim behind that? And the reason why we have to quickly discuss different coordinate systems or non-Cartesian coordinate systems is the fact that differential operators look different in those coordinate systems. So just take the gradient as an example. So here you can see the gradient of gamma, and in a Cartesian coordinate system, the gradient is pretty easy. You just do the partial differentiations of gamma into the directions of x, y, and z, and multiply that by the unit vectors of said Cartesian coordinate system. You should know that if you want to calculate the divergence of gamma, you do it according to this formula. But if we switch to cylindrical coordinates, the gradient and the divergence are going to look different. The exact formulation is given here, and you can see that they differ in the second component, which is the component phi. For this course, it is enough to know that the differential operators look different and to be aware how to formulate them in those two coordinate systems. However, if you're interested to know why the differential operators look different in cylindrical coordinates and look exactly like this, please refer to the additional material which was uploaded onto Ilias.